Okay, so far we've talked a bit about what a general potential energy surface looks like, but how do we actually take calculations and figure out what the minimum energy geometry looks like? How would we find this equilibrium geometry that we know is in the bottom of our well? Typically, we don't already have this potential energy surface plotted out for our molecules. I'm showing you a diatomic where we tend to know the shape of the potential energy, but in general, we don't know our potential energy surface for our molecule. So what's our procedure? Basically, we're going to guess some sort of initial structure. So thinking about a diatomic, let's use nitrogen as an example. Perhaps we could say that we will start off with 1 angstrom for the nitrogen-nitrogen triple bond length. Then what we'll do is we'll calculate the energy for the nitrogen at that geometry. So we'll figure out what that energy is. Now that energy itself is not enough to know whether or not we're at the minimum. One of the things we need to do is determine the gradient of the energy. So in other words, the derivative of the energy with respect to the bond length. So how does the energy change when the bond length changes? So for this particular case, we'd have a slope like this. If we wanted to get to lower energy geometries, we'd have to go downhill, moving this way to longer bond lengths. So then at this point, what we can do is guess a new structure that's predicted to lower the energy. So for example, a bond length of 1.04 angstroms, we would predict to fall somewhere around here. And at this point, we go ahead then and move our geometry, calculate the energy, calculate the gradient, and so forth. And then we do that again. Repeat those steps to get a new energy, a new gradient, a new structure. And we keep repeating those steps until we reach a structure where the gradient is equal to 0. When that gradient is equal to 0, that means we're at the bottom of this well. So for nitrogen, that's basically about 1.1 angstroms. Now, of course, we know that molecules beyond diatomics have a bit more complicated potential energy surfaces. So you've got lots of different valleys, lots of hills that represent our transition states. Now, our reactants and our products are these little valleys in our potential energy structures. We've got these, again, these valleys. Now, a minimum energy pathway that connects a reactant and a product is going to have to go over some sort of barrier. This barrier is basically our transition state. Now, we don't want to go the long way around. We don't want to go from this minimum up over this peak and down. We want to go the minimum path, essentially a mountain pass from A to C. So this kind of minimum energy reaction path is often what we end up writing when we write this reaction coordinate with energy. And again, we've got our reactant, our product, and our transition state. So we want to figure out structures not only for these reactants and the products, but also the transition state. Again, I want to mention the fact that these transition states can be called saddle points. The reason being is because they are a maximum in one direction. That is this path from A to C. It's the maximum as you go that way, but it's a minimum in other directions. So if you were to go this direction, you would be going up the hill. This direction, you'd be going up the hill as well. So it's going to be a minimum in all directions except for one, and that one is the direction of the reaction. So we're used to thinking of a transition state as a high energy state on our reaction pathway, but it is still a low energy structure with respect to some of the other structures that are around it. All right, so how can we use calculus to tell us a little bit about our potential energy surfaces and what we need, what characteristics of the potential energy surface are important? So we've talked a lot about minima so far. And so with a minimum, those are going to have a gradient that's equal to 0. So both our reactants and our products have this gradient that's equal to 0. But it turns out that if we were to look at our transition state, this also has a gradient that's equal to 0. So then how do we tell these two types of stationary points apart? Remember again, stationary point means that the gradient is equal to 0. Well, the answer is we're going to use second derivatives. So we're going to be calculating essentially the second derivative of the energy with respect to position. It's a little more complicated than what I've shown here, but for our diatomic, we just have the position. Now we know from calculus, if our second derivative is positive, that's going to indicate an upward facing parabola. So if we take our little upward facing parabola, we can see that around A, we really have a potential energy surface that looks very much like this upward facing parabola. And similarly at C, we also have an upward facing parabola. Now on the other hand, we have a downward facing parabola at B. It tends to look like this. So that indicates then that our second derivative is negative at a transition state, at least again in that one direction for which it's the maximum. Now it turns out that vibrational frequencies are related to those second derivatives. So the force constant is really related to that second derivative of the energy with respect to coordinates. The vibrational frequencies are related to the force constant. So we'll get our vibrational frequency. It's related to the square root of the force constant divided by the reduced mass. So typically, for our minima, we're going to have all second derivatives that are positive. So in that case, k is positive, and that means that omega will be real. But on the other hand, if we're at a transition state where we've got this downward facing parabola, if we put our second derivative in for k, we now have the square root of a negative number, and we end up with something called an imaginary frequency. So oftentimes when we talk about transition states, we'll be talking about the imaginary frequency that corresponds to this motion going over this hill from A to C. So basically, when we want to determine whether or not we're at a minimum, like A or C, or a transition state like B, we want to calculate our vibrational frequencies. If we have one imaginary frequency, it indicates we're at a transition state. We might see that we have more than one imaginary frequencies, which could indicate then that we're at a higher order saddle point. But anyway, if we're intentionally looking for a transition state, then we want one imaginary frequency. But if we're looking for reactants or products, having an imaginary frequency means that we're not at the lowest minimum.